we are going to talk about an experiment where we experimentally determine different parameters associated with a PMMC instrument or a D-Arsenval galvanometer. So let me just call this experiment that experimental determination of the parameters of a D-Arsenval's galvanometer. Okay, what is a galvanometer? This is basically just a PMMC instrument. It is just a PMMC instrument. It is called D-Arsenval galvanometer to honor the this famous scientist. Okay, so before we start the experimental process, let us talk about a bit on the theory relevant to the dynamics of the galvanometer. Okay, so we will use this notation. We will use G to denote the galvanometer constant, which is basically electromagnetic torque per unit current through the coil, flowing through the coil. So this we will call the galvanometer constant G, and this is basically the electromagnetic torque produced per unit current. Then we'll use the symbol C, and we'll call it the restoring constant, or basically this is the spring constant, and this is the torque per unit deflection produced by the spring. So if the coil deflects, that means if the coil turns or twists the spring, then the spring produces some torque, and the ratio of that torque divided by the amount of turn or deflection is the restoring constant. And we will use the symbol J for moment of inertia of the coil and the attached moving system, that means former, pointer, etc., all those things. So it's better to say the moving system, the moment of inertia of the moving system, coil, pointer, frame, everything. Okay, now we will use the symbol S for sensitivity. So this is what? This is basically deflection per unit current. So if 1 ampere current is flowing through the coil, then how much deflection will be caused by that current? That is the sensitivity. Okay. Now, what is the dynamics of the system, or the differential equation that governs the motion of this system? So dynamics, this we know, it is something like, first we have to add all the forces that act on the moving system. So there are mainly three types of forces, better to say torques. Number one, torque deflecting, or you can say electromagnetic, which is caused by the flow of current which tries to deflect or turn the coil, plus torque controlling, or you can say restoring. This is the torque caused by the spring which tries to hold the coil at its zero position, plus de-damping. Okay, and this is the force which is generated only during the movement of the coil. If the coil is not moving, then this is zero. Okay, this tries to bring the pointer to its settled position quickly so that it doesn't oscillate much. And in this experiment, that means in this particular galvanometer, we will use eddy current damping mechanism. Okay, so these are all the three forces that act on the coil. So they together should be equal to the moment of inertia J multiplied by the angular acceleration d2 theta dt2, where theta t is time obviously and theta is the angle of deflection. Okay, cool. Now let us write the expression for these different torques. First this is T restoring is what is spring constant C, that was our notation. Restoring constant or spring constant is C. So this multiplied by theta, angle of deflection, and this acts always in the direction opposite to the deflection. It always tries to bring it back to zero position, so I will use a minus sign. Now T electromagnetic or T deflecting is what? Is G times I. G is the torque per unit current multiplied by the current is this Gi, and T damping. Okay, so this will be some constant, let me call it B, multiplied by the velocity, angular velocity of the coil, and this will again act in the direction opposite to the velocity. It always tries to stop the velocity, so I'll use a minus sign. Okay, now let us find the value of T damping when we are using eddy current damping. Okay, so if we use eddy current damping, let me draw the schematic of the instrument very quickly. This is my coil. So the coil is wound around this former, and we have flux lines passing through the coil. If the flux density is B for flux density, then and if this coil is rotating with a velocity d theta dt, this is the angular velocity. Okay, if this is the angular velocity, then d theta dt multiplied by r. R is the radius, r for radius is the linear velocity. Okay, now this is the linear velocity of this side. So the induced EMF here will be how much? It will be BLV. So EMF per conductor side will be B multiplied by L, the length. I think it's obvious, L stands for length. BLV, velocity, is given by this, R multiplied by d theta dt. So this is the EMF per conductor side. When I multiply this with 2 into number of turns, N is the number of turns, and there are 2 sides per turn, so a total of 2n times this will be the total EMF. So total EMF will be 2n multiplied by BLR d theta dt. Okay, now 2LR together is the area of this coil. So I can write this as B, 2LR becomes the area times N times d theta dt. Okay, and so this is the total EMF. So and now if the coil resistance is equal to RC and external resistance is R, let me call it R O for outside. Okay, this is the external resistance. Then the current that will be caused by this EMF is given by this EMF BAN d theta dt, the whole divided by RC plus RO. And if this is the current, then this will again produce some torque which will oppose the motion of this coil. So the torque will be, so I'm not deriving this expression because we have done it several times. So torque is always BANI. Now I is this, so in place, and this is also equal to GI, where G is this, so this is G. So okay, if so, then the torque, opposing torque or damping torque, so damping torque will be how much? BAN, in place of I put this value, so I have one more BAN, so it becomes BAN square d theta dt, whole divided by this term RC plus RO. Now BAN square is G, so this becomes G square d theta dt whole divided by RC plus RO. Okay, so this is what? This is the damping torque. Okay, now if I consider the damping coefficient B, which is what? This is here. So damping torque is this, some constant times this. So B then becomes this constant, G square by RC plus RO. So this is by definition. I define the damping torque to be some constant times the velocity, angular velocity, and here it comes out that that constant is equal to this. So this should be B. Okay, and minus sign is only to take care about the direction of the torque, which in this derivation I haven't considered. So this is B, is the damping coefficient. Let me just call it damping coefficient. Okay, now if so, let me then write the dynamics, the equation of dynamics once again, which was here. The three torques sum up to this acceleration times moment of inertia. So then I can write first T deflecting, which is equal to Gi, okay, Gi, then I write T restoring, which is minus C theta, then I write T damping, which is minus B, and B is here, okay, B is here, so I write in place of B G square by RC plus RO d theta dt, and this should be equal to what? J theta double dot, which means d2 theta dt2. I'm using the short notation because I'm running out of space there, okay. So this I can rewrite or reorganize like this. So I take all these theta related terms on one side, so this becomes J theta double dot, then plus this term plus G squared by RC plus RO d theta dt, okay, and then plus C theta is equal to Gi, right? So this is the equation of dynamics. Now from this, what do we see? Okay, now if we solve this equation, there will be two parts, you know, a natural response and a forced response, and then depending on the characteristic root of this equation, the response can be oscillatory or can be damped. All those things are possible. So now what I do, okay, I first make a few observations. First, okay, what are the characteristic roots of this equation? So that is given by, if I call these three terms A, B and C, so that will be minus B, minus of this rule, minus of this term, G square by RC plus RO, plus minus root over square of this G square by RC plus RO whole square minus 4 AC, which is J C whole divided by 2A or 2J. So these are the roots. Now observe that if RC plus RO is very, say, small, so this term is small, which means this term is very high, okay, and this is obviously a positive term, it's a square, so this is a high term minus something, so that will remain positive. If that remain positive, then the characteristic roots are real, not imaginary. Okay, if this is small, then characteristic roots are real, which means implying no oscillation. So if you So the solution will be of the form e to the power this root times t, and then there is no imaginary term, so there will be no sine or cosine term. It will be purely exponential, so there will be no oscillation at all. Okay. Now if RC plus RO is very high, this is very high means this is a very small number close to 0, and then this is minus, so this will be imaginary. Imaginary means roots are complex, which will imply oscillation. So in summary you see that if this is small means what? It's like almost like maybe these two terminals are sorted. If this is sorted, that means RO is 0, so that's the then this is small. So so that means if external resistance is sorted, then it is very small, then no oscillation, then no oscillation. Okay. Similarly, if the external resistance is very high, say it's open, if external resistance is open, then oscillation. So whether this coil will oscillate or not, that depends on this resistance value. Okay, so this is the dynamics, and this is the conclusion that this coil can oscillate or may move to its final position smoothly depending on the value of the resistance. Now, when will this characteristic, this term will be 0? When this is equal to this, and that is the situation when we call it critically damped situation. Let me repeat. Observe that when this is when external resistance is small, then this is positive, this term is positive. If external resistance is high, then this term is negative, and if it is negative, then oscillation occurs. If it is positive, then oscillation doesn't occur. At some value of this external resistance, this is just 0. Okay, so that's the point between the situation of oscillation and no oscillation. So that particular value of the resistance, we'll call it the critical resistance or boundary resistance. So if you increase the resistance slightly, then it will oscillate. If you decrease the resistance slightly from that value, it will not oscillate. So the critical resistance is given by the situation when this term is 0, g square by rc plus ro whole square, g square by rc plus ro whole square minus 4jc is 0, which means this is equal to 4jc. So this is the critical resistance condition. So this implies that g squared by rc plus ro is 2 root jc, and this implies rc plus ro is equal to g squared by 2 root jc. Okay. Further, we know that, say, if RO is infinite, okay, if it is infinite, then this term is 0, or the damping is 0. So then this implies no damping at all. Okay, and at that situation the dynamics will become like this. So this term will be 0, remaining terms will be there. So this term is 0, other terms will be there. So that will become like this. J theta double dot plus 0 plus C theta is equal to Gi. Now, what are the characteristic roots of this equation? They are, so the roots are plus minus root over C by J, okay, multiplied by I, which is I mean square root of minus 1. Okay, so that will be, those will be the roots. So the solution will be will have terms like e to the power, I mean plus or minus this thing, root over C by J I T. So there will be two terms with two constants, and then if you just manipulate them, it will come up with two terms, sine and cosine, that you all know. And this will be so you'll have terms like sine or cosine. I'm not doing the detailed derivation here because that we will do in the theory class, and you also know it from your previous signal networks course. So that will be of this form, omega t, sine or cos. It can also have some phase, etc. But this omega will be this root over C by J. Okay, so that's what we call is the natural frequency, or this is the frequency at which the instrument oscillates when there is no damping at all. So this is the natural frequency, natural angular frequency, and from this we can write the natural time period. Omega is 2 pi by t. So this is equal to root over C by J. So then t comes out to be 2 pi root J by C. So this is one expression that we know. Okay. Now what else do we need? Let us write the equation for sensitivity. This we know that at equilibrium, at steady state, Gi electromagnetic torque is equal to C theta restoring torque, which implies theta by I, deflection per unit current, is equal to G by C, and this is the sensitivity. Okay. Now the goal of this experiment is as follows. The goal of the experiment is as follows. So this is the equation of the dynamics of the moving system, and here you see that there are some coefficients like, or let's look at this version of the equation. So you have the coefficients like J, C, G, and this one. Now if we know J, C and G, this is also known, because G is known and RC and RO can be measured easily, resistance can be measured easily. Okay, so if we know J, C and G, then we know all the parameters related to the dynamics of this system. Okay, so the goal of this experiment is to find the coefficients of dynamical equation, and so this involves determination of or estimation of three parameters J, G and C. G, C and J, three parameters. Okay, so three parameters are unknowns to be estimated, and see right at this moment we have three equations involving these parameters. One is here, G by C equal to S, where this S is the sensitivity. This is what deflection per unit current. This can be measured easily. We'll do it. This is another equation. This I can call it equation 1. This is another equation where the left hand side time period, this can also be measured with a stopwatch or something with the outer circuit open. So we can measure the natural frequency or natural time period, and then we have J and C related to each other via this T. So this is equation number 2, and here we have another equation involving J, G and C. The left hand side can be measured. So this left hand side is the resistance of the coil which we can measure, plus the resistance of the external circuit also that is measurable, and this is true only when the moving system is critically damped. Okay, so these are the three equations that we have, and from these three equations we have to find these three unknowns. Okay, so now we have to do some algebraic manipulation so that we can write this G, C and J in terms of these things, the known quantities like S, T and this. So these are the known quantities. In terms of that we have to write this G, C and J. Okay, now let's do this algebraic manipulation. Okay. This manipulation you can do it in your own way. There can be many possible ways. I'm just trying to do it in one way. I actually took a small pause in the video, in this recording, to find some way out, and I will do now it in this way. So I'll start with this equation. I'll write G square by 2 root J root C. This is equal to RC plus RO. Now I will multiply this with root C in the numerator and denominator. So this will become like this, G square root C by 2 2 root J and C. Okay, now we see that G by C, which I can take 1G and this C and write that as S. So this I can write as 1G by C becomes S, and I'm left with 1G multiplied by root C by root J, root C by J, and a 2.5. Okay, now here this I can now write this term using this equation, that root C by root J, if I bring it this way, will be 2 pi by T. So this will become SG, this term will become 2 pi by T multiplied by half, this half as it is. Now this 2 cancels, so I'm left with this SG pi by T. So let me come here. So I have this thing RC plus RO, RC plus RO, this is equal to this SG pi by T, SG pi by T. Okay, so now I can write G as RC plus RO multiplied by T whole divided by pi and S. Okay, now the right hand side, all these things are measurable. We'll measure all these things. This time period is measurable, sensitivity S is measurable, this resistance is always measurable. This is the resistance under critical damping. Okay, so this is the resistance under critical damping. So RC plus RO is under critical damping. And this T, this time period, is without any damping. So this is the natural frequency under no damping at all. So you have to measure undamped, completely undamped time period and the resistance which causes critical damping. Sensitivity can be measured, pi is a constant, so we can find G. So one parameter is already solved. So G is solved. Now you have to find C and J. Okay, so this is one equation to find G. Now how can we find C? C is very easy now. We see that C is, from this equation, C will be G by S. So C is G by S. So which will mean is this RC plus RO multiplied by T divided by pi S. This is G, and one more S, this will become S square. Okay, so this is another equation. This will find C for us. Now the last thing we have to find is J. Okay, now how can we find J? Maybe this one. This one will be easiest, I hope. So if I start from here, let me take a square. So this will become T square is equal to 4 pi square J by C. Now C is known, J is the unknown, so let me write J as T square C whole divided by 4 pi square. T square C by 4 pi square. Now C is already resolved, so I will put the value. So T square by 4 pi square as it is, and C I put the value from here. RC plus RO T by pi S square. So this will be T cube by 4 pi cube S square, and here RC plus RO. Okay, T cube RC plus RO 4 pi cube S square. Yeah. So this is another equation. This is T. Sorry, this is J. Okay, so we can find all these parameters J, C, G, which are the parameters in this dynamic, in this equation of dynamics. So now once we have these equations, we understand the dynamics of the system in all the possible detail. So last task that remains in this video is to talk about how to find these terms, this resistance, this time period, and this sensitivity. Okay, these three we will find experimentally, and so once we find these values experimentally, then these equations which we have derived theoretically, mathematically, will give us the desired unknowns G, C, and J. So final part of this video is the determination of these three unknowns: this critical damping resistance, this natural time period or frequency, and the sensitivity of the instrument. Okay, let us first draw some circuits. The first thing that we need is definitely the galvanometer, G for galvanometer, and this is the instrument of which these parameters J, G, C we want to find out. So this is obviously the main component. So this will have two terminals for the current to come in and go out, and then we need to apply some voltage across this so that current flows. So we need a voltage source. So we will have a voltage source. Let me draw it here. Let it be a constant voltage source, 2 volt plus minus. So I can connect these two terminals to this. However, in my experiment I might like to apply different values of voltages to the galvanometer. I may need to change the applied voltage. So for that I can either have a variable voltage source or a signal generator. That is one option instead of this constant voltage source. Another option is just to use a potential divider. So I can use I can just connect this to a potential divider like this. So basically I will. So now I'm taking only a fraction of this total 2 volt here, and this I will connect to the galvanometer, the other end. So this now, as I move this position, I can change the voltage applied to the galvanometer. But in our lab, in our experimental setup, this potential divider will have a bit more sophistication, which is as follows. We will here connect a variable resistance. Okay, and this variable resistance can vary from 0 to 10 kilo ohm in steps of large values. I do not know the exact values, maybe 1 kilo ohm. And this part, this is also a resistance box, variable resistance, This can change between 0 to 1 ohm, I think in steps of 0.1 ohm. So what it helps us in, this resistance helps us in changing this current in a coarse way, in large steps, and this resistance box helps us in changing this potential in small steps or something like that. So these two together you can adjust to adjust the voltage that will appear across these two terminals. Okay, so basically we have two controls just to control this one voltage. One can control the voltage in large step, another can control in fine steps. So with one you can change the voltage quite fast, and with the other one you can change it very finely in small steps. That's the difference. Okay, so this will be, so I'll connect this. I have to connect this so that the current can flow through the galvanometer, and I can also have a key here, so that only when I want the current to pass, the current will pass, otherwise it will not. Similarly, I can also have a key here. Okay, so this is one more key. So now this allows me also to turn on and off this power supply when I don't need it or when I need it. Okay, so this is the arrangement so far to apply a variable voltage across the galvanometer. Okay, so now what are the things that I have to determine? Let me first write the things that I want to determine. To determine, one is T, natural time period. Okay, so this, then we need the resistance of the coil plus the external resistance RO under critical damping, and sensitivity S. Okay, let us first start with time period determination. And remember, this has to be natural time period without any damping. So natural time period means no damping. Now no damping means very high external resistance. If we look at the equations here, these are or maybe here we see when the external resistance is very high, B is 0, so then there is no damping. Okay, so external resistance has to be very high or open. So RO open circuited. So RO should be open. That's very important. Under that situation, we have to measure the time period. How can we do that? We'll do it like this. Okay, so we will first close this switch. So T determination, of T time period. Number one, step one, close this switch. Let me give it a name, K1, K2. You can keep K1 always on. You'll only lose some power, or it's fine otherwise. Now K1 it's always on, fine. Now close K2. Okay, if you close K2, then current will flow through the galvanometer, and you can adjust this jockey to have a desired amount of deflection or desired amount of current through this. But important thing is, first close this K2. So this, what this will do, this will bring your pointer to some value. In this experiment we will have light pointers, but okay, this I can schematically draw it like this. There will be no real pointer, okay, but there will be some light beam moving on a scale. But okay, this is fine. So this is 0 position. The light beam will move to some value, positive value, when you close K2, and it will settle there. Okay, now when this is settled, when this is steady here, at that instant open K2 suddenly. So then what will happen? There is now no current. So which means this pointer should come back to its 0 position, because now there is no current at all. But now what will happen, when it comes from here to here, it can overshoot. It can overshoot, come back, and again it can oscillate. So it will oscillate. Okay, and now note that when this is oscillating, K2 is open. K2 open means what? The external circuit is open. The galvanometer is not connected to anything. This part is a separate part. There is no closed circuit through the galvanometer. Okay, now no closed circuit through galvanometer, through galvanometer G. So which means RO, so this means RO is equal to infinite. So this is completely undamped situation. There will still be some damping due to the friction in the bearing, etc., which should be very small. Otherwise this is absolutely undamped. There is at least no eddy current damping. So now you use a stopwatch and measure the number of oscillations in a given time, or measure the time for a fixed number of oscillations. I don't know, 5, 10 oscillations, how much time it takes. That will give you time period T. So this is how to determine the time period T. This is done. Okay. Now next, let us try to determine this thing, RC, the coil resistance. Okay, RC determination. So like any resistance, you can determine it with a voltmeter ammeter method. You may use a voltmeter and an ammeter. So basically pass some current through it, measure the current with an ammeter, measure the voltage across it with a voltmeter, divide the voltage by current. Ohm's law will give you the resistance of the galvanometer. Like any other resistance, you can measure it in that way. But in this experiment, we will do it in a different way. In this experiment, we do it differently, because we can do it without even having a voltmeter and ammeter. It's not at all required. If you want to use a voltmeter and ammeter, you need them, but we can do it even without that, much more simply. How? Here it is. So what I will do, I will connect a variable resistance here. Okay, let me call it R. So this is a variable resistance in this circuit. Okay, now what I will do, I will first, so the steps are, first set R equal to 0. So there is no resistance at all. Close K2 key and observe deflection. Okay, and at this moment you can adjust this jockey so that you have a desired value of deflection, some amount, I mean maybe full scale or something like that. You can adjust this, or okay, so maybe adjust option that if you want, adjust voltage to have full deflection. Okay, say not necessarily full deflection, any amount of deflection that you want. So adjust that. Okay, now step 2, increase R, keeping voltage applied voltage constant. Okay, increase R so that the deflection is halved. Okay, so if you had full scale deflection in step 1, now increase R so that the deflection becomes half in the galvanometer. Now half deflection means what? Definitely half amount of current is flowing compared to step 1. Half amount of current means what? It means the resistance here in this path consisting of this galvanometer and this variable resistance R is doubled. Only if this resistance is doubled, then only this current can go half. This voltage applied is kept constant. So this resistance, this total resistance is doubled. That's why the current has become halved, and that's why the deflection has become halved. So that means now this resistance should be equal to the resistance of the galvanometer, because these two together is the double of the galvanometer alone. So now R is equal to RC at this point. Okay, so you see that we do not need a voltmeter or an ammeter. We can just watch the deflection in the galvanometer, because we anyway have a galvanometer. Why do we use an extra voltmeter or ammeter? And we will anyway need variable resistance for other parts of this experiment. So why do we need an extra ammeter or voltmeter? So this way we can use determine the resistance of R of the galvanometer. Okay, there is a small observation that for this method to work, which also is known as half deflection method, let me write here. Okay, so here we need the voltage applied across this to stay constant. Okay, so that's the assumption, keeping the voltage constant. Now we can argue that no, this voltage is actually not very constant, because I'm changing this circuit, I'm changing this resistance, so this arrangement will not keep the voltage at this between these 2 points constant. But I will say that observe that this resistance is actually very small compared to the other one. This is of the order of kilo ohm, this is of the order of ohm. So no matter what happens to this part, the parallel combination of this and this will still also be of value similar to this, provided this resistance is quite higher than this resistance. In that case, this voltage will remain constant. Now in your discussion in your lab report, you may just do this analysis, because when you do this experiment, then at that point you will know the value of this resistance exactly. You'll also have the estimated value of RC and this R, which right now I do not have, and that at that point you can actually do a estimation with your calculator that was this voltage really constant, or if not, how much was the change, was it small, was it large. You can do this thing in discussion. So one point here in discussion you may like to do it is this voltage, if I call it V, is V kept constant during RC determination. So this you may like to do in your report. Okay, cool. Now next is determination of RO for critical damping. Okay, so we will modify our circuit a bit. So here is the previous circuit, and let me do the modified circuit here right in front of you. So this first I need this variable voltage source, so which will be like this. Okay, so this is the variable voltage source. Between these two terminals I should have the galvanometer, and then definitely I'll have a key. Okay, and so if I close this, there will be some current through it. If I open it, there will be no current through it. Now the modification that I will do is this: I will put a variable resistance here, right in parallel. I mean, here it looks like parallel, or it's actually in series. Wait. So okay, so there will be a resistance. Now let's see what happens. Okay, let me call this. Let this be always closed. K1 is always closed. This is K2. Now observe, if K2 is closed, then this current that comes from here, part of it goes through this resistance. I'll call this RO, and this resistance, coil resistance, I'll call RC. So part of this current goes through RO, part of this current goes through RC. Here they join and go back together. Then RO and RC are in parallel. RO and RC in parallel. Okay. Now if I open this K2 switch, when K2 is open, then here in galvanometer circuit, so galvanometer is now completely disconnected to this part, upper part, and galvanometer is only connected to this RO, and here they are in series, so there can be only a current, same current that flows through both of them in a circular way, maybe like in this way or maybe the other way, but same current flows. So now we can call that RO and RC in series. When this K2 is open. Okay, so now for the experiment what we will do, the steps are: number 1, close K2. So when I close this switch K2, what happens? Some current flows through both of them, through RC and RO, and it continues. Okay, and so there will be some deflection. So there will be some deflection, non-zero. Okay, now then open K2 suddenly. Now if I open K2 suddenly, then what happens? Assuming no inductance in this or negligible inductance here. So what happens? This part, this potential divider and the voltage source arrangement, this will not be able to drive any current through either RC or RO, through galvanometer or this resistance. So this part is completely out of this circuit. So if I open it suddenly, then the pointer must come back to 0. Okay, so it must come back to 0. But now it can oscillate, come back, go back and forth. Okay, and while this coil is oscillating, when this pointer is oscillating, means coil is oscillating, then the eddy current that will be generated in the coil will now have a closed path through this RO. So that can flow either like this or like this, depending on the direction of the motion of the pointer. So when maybe when the pointer is moving from here to here, in that case, if current is flowing in this direction, then it will flow in the other direction when the pointer is moving from left to right in the other way. Okay, so now that eddy current flows through RO and RC. So the total resistance against eddy current is RC coil resistance plus RO. Now you see, I can have high RO. If I have high RO, that means this is almost open, or very high resistance, then the eddy current is small. If eddy current is small, eddy current low, implying low damping, and if low RO, so then high eddy current, high damping. So for high RO, you can have underdamped condition. Here you can have overdamped. Okay, so what you can do, what you have to do is this. You have to first do this, open K2 suddenly and check, is it underdamped, is it overdamped. Say it is overdamped, say it is underdamped. Okay, in that case, you suppose when you do this step 2, when K2 is opened, you find it underdamped. Then what you have to do, you have to lower this resistance slightly or by some amount and do these 2 steps again. Then lower RO, okay, and repeat 1 and 2. So close K2 and open it suddenly. Now if you see that this is still underdamped, you have to lower it again and repeat 1 and 2. Keep repeating this process until at some value you find that no, this is not oscillating anymore, you can then adjust the RO of bit more finely, increase slightly, decrease slightly, and find the value of RO for critical damping. So that is how to determine the value of RO for critical damping. So this is done. Final thing, that final unknown that we need to know is S, determination of S, sensitivity. This is what? This is just nothing but deflection per unit current. So this is easiest, I need not talk about it much. You just have to know just need to have some known current flowing through the galvanometer and observe the deflection angle. So measure this deflection. Remember, deflection in radian. Okay, so we can in our lab we will see that there is a light pointer which moves along a scale, so that gives deflection in millimeter or centimeter, that you have to convert into radian. That's very easy. As soon as you see the setup, you will know how to do that. Okay, so do that, but this deflection should be in radian, because all the theories that we have done before, everywhere this sensitivity was assumed to be in radian per ampere. So this has to be again in the same unit, otherwise those equations won't be valid. Thanks for your patience. Have a nice experiment in the lab. Thank you.